Good morning, good afternoon, and good evening to everybody. As Alex said, this is part 7 of the high voltage DC series. The first 2 covered a brief introduction to high voltage DC and a deep dive into some of the technical elements of the building blocks for high voltage DC distribution and conversion. We then had a series of guest speakers from Hewlett-Packard, Emerson, Universal Starline, and the Fraunhofer Institute, and got some exciting news later on in this presentation of an additional guest speaker to round out the series next week. So, looking at hybrid transportation, that's a very wide topic. In this case, we're covering everything from passenger cars up to earth-moving equipment. So hopefully we'll be able to cover a lot of ground. We've tried to include a lot of links for further reading, and I've tried to include the source wherever I've acquired something from the internet. So let's kick straight off into the hybrid market. Now, the first thing to note is that hybrid vehicles, whether they're partial hybrid or full electric, really fit into a larger holistic picture of energy usage. This actually overlaps very well with the 380 volts microgrid seminar that was given by the Fraunhofer Institute a couple of weeks ago, in that we've got the car as an essential building block or an element in the ecosystem, whether that's obviously as transportation, but as a load or a source or a storage for power, obviously electrical power. And this picture taken from the Toyota site reflects how a car on its own, or a larger bus or truck for larger facilities, we can intelligently charge that device at times when electricity demand is low, therefore helping to smooth out electrical supply and demand. Wind power is great if it's windy. Solar power is great if the sun's shining. And nuclear power is great if you've got a steady load on that, because you don't want to turn it on and off. By using all of these electrical generating sources and then using that electricity in different ways that we can time across each 24-hour period, then we can make most use of the electricity. We can de-stress any electrical distribution points or infrastructure throughout each country. And also, in some cases, if there is an incident, let's say an earthquake, obviously for the people of Japan, this is at the front of their minds often, using the car as an emergency backup to power your house, or if it's in the case of a truck or a bus, maybe power a larger building such as a small hospital, clinic, or school. So the car is an essential part of an ecosystem that we're moving towards. And this is not just a Japanese view. The same kind of picture is represented by companies like BYD from China, like Ford in the US. It's very much a global view. So if you do want to learn more about the microgrid, that was back in seminar number 5, and that is one of the ones recorded on the website. Now, where are we going with electric or hybrid vehicles? This picture from Continental shows the adoption of electric hybrid technology across time. And you'll see that by 2025, which is only a few years out when we think of large infrastructure or large systemic changes, they estimate that 30% of the vehicles in the world will be hybrid of some kind. And just to highlight the other large chunk there, the light gray start-stop, this is using electronics to detect when your car is stationary and turn off the engine, and then imperceptibly to turn that engine back on as soon as you press the accelerator pedal. So this is actually now very, very broadly adopted in Europe. I would say 50% of all new cars are containing this stop-start mechanism. That's an internal combustion engine-driven device, but it's using electronics in an intelligent way. So back to the hybrids, whether it's full electric or partial, estimating 30% of the vehicles in 2025. In addition to any discussion about the economy or the environment of electrical vehicles or hybrid electric vehicles, as we go through the examples, please also look out for design changes where going to a hybrid or a full electric makes a significant change in the physical structure of the vehicle to overcome previous problems. So with a clean piece of paper and some new technology, it's amazing what you can do. Now, for this seminar, I'm saying that a hybrid is a mix of an internal combustion engine and an electrical motor, and they'll be arranged in different ways. So just to clarify, we're looking at either gasoline, i.e. petrol, or diesel engine coupled with an electric motor, or we do in some cases refer to a pure electric. So that's what I mean by hybrid in the sense of this presentation. And there are certain different ways that the powertrains fit together, which we'll go into in the next couple of slides. So the first one is the series hybrid. Now, the idea of having an internal combustion engine followed by an electric motor is not new. In fact, I would say that if we look at railway locomotives, the diesel electric has been at the forefront of many railway systems around the world since probably the 1920s or 30s. So having that internal combustion engine drive an electric motor and the flexibility that offers is not new. The real key here is that we're applying that technology to a much physically smaller vehicle with obviously tougher price points, different usage, and also now we're using that development in battery technology to store energy as well. So using the engine to create electricity to be stored, and in this series event going straight down to the motor to drive the wheels. So this is the series hybrid, and this was probably the first real look at hybrid systems. Now moving on, we've got the parallel hybrid. In this case, you've got the internal combustion engine directly driving the wheels. You've got a separate electrical engine, again, directly driving the wheels. And obviously in all of these cases, we've got regenerative energy going back up to the battery. So as you're coasting downhill, you turn off the engine, your motor runs in reverse, or you use the energy of the motor running to create electricity, which is then stored back in the battery. So this is the parallel hybrid system where you've got two separate powertrains going to the main drive. And then the last variant is the series parallel, which is the dominant technology used across different car manufacturers today, in that we've got obviously the internal combustion engine, which can drive the axle directly, an electric motor which drives it directly, but there are points in time, whether it's on the aggressiveness of the driver or the conditions in which he or she is driving, will dictate whether one or both engines or drivetrains kick in at the same time. So here we obviously have the internal combustion engine can generate electricity, which is stored in a battery, which then goes down, but also it has its own mechanical direct linkage to the axle. So a few different ways to look at that. Now, before we go into the drivetrain itself, we need to look at battery technology. And this gray table on this page is sourced from Ford, and it shows the heritage of different battery technologies over time. And obviously, lead-acid batteries have been around for a long time. There are electrical cars that were in the late 1800s, early 1900s, using lead-acid batteries to provide propulsion. As time moved on and we really got into the modern era of the hybrid car, the nickel metal hydride came into use. However, the benefits of lithium ion overtook that, 2 times the energy content, which means smaller, lighter, and also a more predictable technology. So really from 1991 have been the mainstay of commercial use. Having said that, there are some adaptations of lithium ion we should take a look at, and also a note that China's BYD company have what they call a proprietary iron phosphate technology that they use in their vehicles. So I don't unfortunately have details on that, but if there are any battery experts out there, then take a note of the iron phosphate technology. So a few things to note about batteries. Obviously, batteries work with the most output at a stable medium temperature. So systems need to have heating and cooling to keep them within the right range. And just a note, when it comes to the voltage coming out of those batteries, a single lithium-ion cell is about a 4-volt unit. So obviously we need to stack a lot of those to get to higher voltages. And the actual nominal voltage will vary by manufacturer, also by the design and function of the vehicle. So cars are in the 200 to 350 DC nominal range, going up to higher voltages for larger vehicles. It should be noted, however, that because of the potential high charge state and low discharge state of batteries, in a typical automotive application, we might need to run from 190 volts all the way up to 425. So we need to make our converters capable of that kind of input voltage range. So the research on lithium ion, and this is taken from Toyota, looking to take the energy capability of that technology from the 100-watt region, or maybe 200-watt region, up into the greater than 1,000-watt region per liter. And they're looking at 2 different technologies. So taking the image to the top of the page, the electrolyte solution which is surrounding each individual lithium-ion cell, then the first thing is they want to do is take away that liquid, make it a solid electrolyte, kind of a plate, and apply it between the anode and cathodes. That will make everything very smaller and therefore also lighter as well. Or they're looking at doing an air gap, so a lithium air battery. So 2 different techniques that Toyota are looking at to effectively get more energy in a certain volume and therefore more energy per kilogram using this kind of technology. So that's one to look out for lithium ion. Now, we can't leave behind battery technology without thinking about the environmental and human issues involved. Much in the same way as we in the electrical industry are very familiar and need to be very careful about our raw materials, such as the rare earth metals and materials going into tantalum capacitors, for example. We need to make sure that we are environmentally responsible and also socially responsible, to make sure that the material coming from various parts of the planet is not created through any form of exploitation. So the first one on the environment, whether it's the European Union with the directives of end-of-life recycling, or it's commercial groups such as those in the US, the End-of-Life Vehicle Solutions Corporation, getting together to make sure that the lithium does not enter the ecosystem, being able to trap that, capture it, recycle it. And also in the supply chain, the notes here refer to some work by Ford Motor Company in making sure that the materials that we obtain are obtained fairly. So that's one thing to note. So going into some examples on hybrids. The first one, going to, I think, the real pioneer in modern-day hybrid technology is Toyota. And this is a look at their power control unit, which for them, in their systems, is the heart of the matter. So this combines a couple of different functions. We've got an inverter, a boost converter, and then a DC-DC converter. So obviously we need to take power from the battery, create enough voltage to go across the motors for the wheels. We also need to have a system that takes energy back from the wheels and converts it back into the high voltage battery. And then the DC-DC converter, the auxiliary power system, is where we use that energy coming from the 300, 400 volts battery, and we need to convert that down to, let's say, 12 volts, because you still need your radio to run, you still need your seat motors, your windshield wipers. All of those different things are based today on a legacy 12-volt system. So we also need a converter from, say, 300 or 400 volts down to 12 volts. The power of that converter varies by unit. Generally speaking, 800 watts to 6 kilowatts covers a very broad range. Traditionally, a domestic passenger car has been in the 1.8 to 2.4 kilowatt zone. And we'll go into that a little bit more detail shortly. Before we leave Toyota, and as an aside, and this may help the adoption of electric technology, pure electric technology, is the realization of wireless charging. So across the world, a few different companies are looking at wireless charging. Toyota with the Prius, they have a couple of these guys. I think the plural of Prius is Prii. So there are 3 Priis in the Aichi prefecture in Japan in a year-long trial, where there is a coil that's embedded or situated in the parking spot, and another coil within the trunk of the car. And by magnetic resonance, the car is charged just by being located over that spot. And they've got their intelligent parking assist technology to make sure you get right over the emission of that energy. They're not the only company. Volvo and Qualcomm Halo have different systems. And if you're listening from the UK, the city of Milton Keynes in January started a trial, hopefully it continues, of pure electric buses going around a 24-kilometer loop of the city. Every time they come to a bus stop and people get on and off, the bus is charged from an induction coil underneath. So that we wish that one the best of luck and hope that's a great pioneer for systems to come. Staying in Japan and moving to Honda and taking a look at the selection and choice of engines or motors depending on the load. And whether it's a pure electric, and in Honda's case they have a car called the Honda Fit, which has a pure electric option, all the way down to the bottom of the page there, which is the sports car, the NSX. Choosing the right powertrain, choosing the right motors is key for success. So in this case, there can be a pure electric or a combined electric gasoline engine. We can have 2 motors, which are physically separate. And I think the interesting one is for the NSX at the bottom there, we have a petrol engine, which drives the front wheels, and then physically separate 2 independent electric motors which drive each rear wheel. So in this case, you've got a hybrid technology, so you can run or maybe limp home if something goes wrong using either engine. You also have automatic 4-wheel drive. You can very easily control any traction control. And it also means that for the construction of the device, especially a low-slung sports car, suddenly there's no prop shaft and no diff. So you don't have that weird bulge in the middle of the car. So this is a very interesting use. Again, this is one of the examples where we look at new technology and with a clean piece of paper think, how can we redesign things to make them better? So I think Honda have done a really good job there. And one of the other things to look at in this particular example of the Honda Fit is how in the central picture they've taken the transmission, which is required for a standard gasoline engine, but they've integrated the electric motor in it. So saving weight, looking at how to design something in a very elegant and efficient way. So these guys, I think, again, Honda have done a really good job here. Moving across to Europe, and this BMW example is a look at economy and also performance. So again, depending on the style of driving, if you're being aggressive or conservative with your driving style, or if the conditions change, then this BMW example, the 7 Series comes with what they call the active hybrid option, and there's a mode that goes to maximum efficiency, pure electric drive. There's also a mode, if you're feeling wicked, to go to the Sport or the Sport Plus mode, where you get the full power from the straight 6 twin turbo, and you can even get an extra 40 kilowatts from the electric boost. So in this case, you can flick between economy driving or real performance driving. The other thing to note is that for all of the manufacturers, they guarantee a minimum lifetime, usually a mileage or a kilometer use, as well as a life of the batteries. And all of these manufacturers do have recycling programs to take back the battery and do something with it. So it's very important that everyone is very aware of the responsibility involved. Now, turning to China, BYD, very, very big car company in China, also a very big battery manufacturer. So they've got some in-house technology. This is where the iron phosphate technology comes in. And I think BYD have done a great job. In this case, the E6 looks like a normal car, has 75 kilowatts of motor power, so it's reasonably sporty. It can sit 5 human adults, and it has a 300-kilometer range with a top speed of 87 miles an hour. This is a legitimate car without any of the restrictions of previous models in terms of size or range or top speed. So I think in this case, they've done a really good job. And as part of their promotional material, they refer back to that microgrid emergency standby, and they actually quote how long a house can be run using this kind of technology. So in a 12-kilowatt usage house, you can keep that thing running for 5 days using a fully charged E6 engine or car. So I think as we're going through these, you're seeing hybrid is more and more the everyday choice without limiting factors. Another example where, with a clean piece of paper, you can change the design is in this full electric bus, again from BYD. So, same iron phosphate battery technology, and in this case, we've got independent motors on each wheel, which means that you don't have to have that centralized spine of mechanical transmission through the bus. As a result, you can drop the floor of the bus. Therefore, clean piece of paper thinking, people can get on and off much easier, which also means that within a standard loading gauge, you can actually increase the height within the bus so you don't have to dip your head as you walk along. So a good example of with a clean piece of paper using the technology. So that was a good one from BYD. Now, moving up in voltage, again, with military equipment, there is a new standard called the GCS 600A, which refers to a 600-volt nominal battery, or 610 volts nominal, which is used within some prototype systems. The one at the top right is a picture of the ultralight vehicle, which is a research prototype right now, which has that one actually has a Subaru Boxer engine, which is used to create a high voltage DC, and then that goes back through motors also to assist the drive. And then also when we're thinking about hybrid systems, as well as thinking about propulsion, we also need to think about those accessories. In the case of a passenger car, that might be the radio. In the case of a military vehicle, that might be how you turn around the turret with the gun on top. And the Paladin howitzer is being upgraded and going away from the hydraulic system that's been in there since the 60s, 70s to an electric motor-based system. Lots of benefits to this. First is a lot lighter, The second one is it's much easier to maintain because with standardized electric motors, if one fails, you can rip it out and put in a spare in the field and keep running. You don't have to retire to a maintenance base and lose effectiveness in the field. So that kind of adoption of electric accessories is also analogous to the 2 weeks ago we had this seminar on 270 volt DC within aircraft. In that case, the example was Airbus with their electric actuators, electric hydraulic actuators, EHAs. In this case, we're using electricity to actually drive the same kind of system, obviously land-based, not air-based, but the same kind of evolution. And the great news today that we're able to talk about is that next week's seminar, which will close out the high voltage DC series, will be given by a gentleman called George Hamilton, who is the Deputy Assistant Director of the U.S. Army's Research and Development Engineering Command, which is in Warren, Michigan. And next week he'll be giving a presentation on high voltage DC and including a look at the kind of technologies that are involved from a power component standpoint to achieve this kind of performance. And he is one of the gentlemen that's been responsible for the Paladin system, the ultralight vehicle, and vehicles like the Stryker personnel carrier, which have also gone through high voltage DC prototypes. So very excited about that for next week's presentation. Even higher voltage, we're looking at earth-moving equipment. And a surprising and slightly worrying statistic from Komatsu is that for all of the energy contained in diesel fuel that goes into a piece of earth-moving equipment, only 13% of it is actually used to move earth. The rest is completely wasted. So Komatsu have published examples of a hybrid piece of earth-moving equipment. So obviously there's still a big diesel generator in here, but if we think about the accessory systems, things like rotation. So imagine you're the driver of one of these excavators and the machine reaches forward and pulls up a bucket full of earth, and you want to turn to the left 90 degrees. It takes energy to start that momentum or overcome that inertia, and then it takes energy to stop your movement once you get to 90 degrees. This new system uses electric motors, or rather electric motor/generators, and as you turn and come to a halt, that kinetic rotational energy is converted back into electricity and is saved at 800 volts in ultracapacitors, in this case, rather than hybrid batteries. And then when you want to start moving again, the energy is discharged from those supercaps back down through a converter to the motor, and then the unit swings back around. So in this way, this is a great example of how, with a clean piece of paper and thinking hybrid, what does that bring to us? We have a big change in design. At the same time, we need to think about things like air conditioning. So if you're operating one of these devices in the desert and you want to stop to have lunch, then you can turn off the diesel engine because that saves fuel. However, it's going to get very hot. So one of the issues is how do you still maintain the air conditioning system, which might be running from that high voltage DC? And the key to that is our auxiliary power supply that we talked about earlier. Before we leave this page, the Komatsu report had a 25% reduction in fuel and CO2 emissions going to this hybrid approach. So it looks like it's been a success, and we wish them even more luck with the next few designs. So moving to those auxiliary power units. So this is the anywhere between 800 watts and 6,000 watts of power conversion from that high voltage, usually lithium-ion battery stack, down to 12 volts for cars or maybe 24 volts for trucks and buses. And the key here is how to do that in a very small way and a lightweight way and an efficient way to maintain this movement towards more efficient vehicles. So for Vicore, we employ what we call a power component methodology, by which we mean that we have some building blocks, physical building blocks, power modules, and into those modules we can put an array of different topologies, whether that's something with an AC input or DC, isolated, non-isolated, regulated, non-regulated, etc. And we can optimize each of those building blocks. Maybe we optimize for a certain frequency or a certain efficiency at full load or light load energy saving techniques. And they become building blocks. And those building blocks, like Lego bricks, can be used to make systems by different arrangements. So for example, you might have a high voltage DC to 1 volt chain for a data center, for the high voltage DC down to the processor. At the same time, those exact same building blocks can go from 800 volts and be used to provide 24 volts for an earth-moving auxiliary power module. So these very flexible, highly efficient, very small and light building blocks can be used to make some excellent, small, high-efficiency, low-weight systems. And for Vicore, we're focusing on this auxiliary power module rather than any other element of the vehicle. So a quick recap on some of those building blocks. The first is our non-isolated buck-boost regulator. So this, as you can see from the schematic on the top right, is a 4-switch non-isolated regulator. And the combination of switching of those different MOSFETs, either single MOSFETs or paralleled MOSFETs, depending on the power output of the device, go from the buck to the boost or a buck-boost kind of function. A few things to note about this. The first is it's completely zero voltage switching, which means we can run at a very high frequency, which means we can reduce the size of the magnetics, which reduces the size of parasitics, which improves the efficiency once again. So we have this positive spiral of design. The other thing to note is that the sequence of switching of these devices is always the same, but the time period for each of these switching phases changes depending on if we're bucking, boosting, or simply passing straight through. So in this case, we have a glitch-free or hysteretic-free transition between bucking and boosting, a very, very flexible item. The other element we've got here is our DC to DC transformer. So this is our voltage step down or step up with isolation unit. In this case, we're saying it is our sine amplitude converter topology. And the reason it's a sine amplitude converter is because we put in DC, we switch the MOSFETs on the primary side to create a sine wave that crosses the transformer gap. And on the secondary side, we do full wave rectification back to DC. It's called sine amplitude because the amplitude of that wave changes with load. So as the load increases in step function, the amplitude also changes. So that's the reason for the name. Again, this topology is fully zero voltage switched and also zero current switched. Again, we can crank up the frequency to about a 1.7 megahertz level for these devices. A few other things to note about this topology. The first is because it is an isolated transformer design, we can stack inputs for higher voltage, and we can parallel outputs or inputs for higher power as well. So it's a very, very flexible building block. One other thing is that this is reversible. If you put in 380 volts, you might get 48 volts out if the K factor is 1 divided by 8. If you put in 48 volts on the right-hand side, you get high voltage on the left-hand side, so a reversible topology. It becomes very difficult to talk about primary and secondary in this case. And the third thing is that because this is a fixed frequency LC resonant converter, we're not actually storing any energy within the converter on any one switching cycle. As a result, the device is thermally limited and not current limited. So there are applications which have pulsed power, and we can do a 2x overpower before we have to limit the current going out. So a very, very flexible tool here. And the first of these devices in what we're calling a 6123 package was released late last year, and that's the 1.2 kilowatt 384 to 48 volt device. We're also looking to increase that power and also come out with more different K factors down to 12 volts or 24 volts, etc. So those are 2 building blocks, and more information on those is contained in Seminar 2. Putting them together and addressing one of our applications, this is starting with the high voltage, earth-moving kind of voltage, that 800 volts, and needing to get down to 24 volts. You can see in this simple schematic how we're stacking 400 volt input bus converters to get that 800 volt standoff. At the same time, we're paralleling the 48 volt outputs. So in this case, we're going 800 volts down to 48, and then we're using our non-isolated regulator to correctly charge the 24 volt battery. To the bottom right, we also have an auxiliary 12 volt load through a similar kind of system. When operating in reverse, we're using, as you can see, a bypass diode around that converter, and then we simply put that voltage into the base of the converter, and then we get the high voltage out. So obviously this system, the upstream devices running from that 800 volts are actually quite rugged, and they can run at half the voltage depending on how we implement it. So in this case, working with the customers, we need to regulate downstream, but we don't need to regulate upstream. Therefore, we can actually have a much more efficient way going back uphill. So this is an example using those building blocks in different ways for a hybrid transportation system example. And the photographs on this page show the prototype that we've been running. So you can see on the left-hand side at the top, those are the 4 bus converters going from 800 down to 48 volts. And then we have the rack of 12 regulators going down to that 24 volt point. So a very, very simple, elegant, and small design. This is only 3 inches by 12 inches. Obviously, you need a heat sink on the top. In many automotive applications, that can be a liquid-cooled cold plate. So a very slim, high-power, high-efficiency design. Introducing another of the building blocks, we have what we call a DC ZVS. That's a double-clamped zero-voltage switch converter. This is an adaptation of the previous 2 topologies. So we're looking at the non-isolated buck boost, and then we change the inductor into a transformer, and the second half of it becomes the same as the transformer basis. So here we end up with a regulated, isolated, and stepping down converter. It's not quite as efficient as the previous systems with the individual components, but at the right power level, it makes perfect sense. And we can achieve up to 94% efficiency in a typical automotive environment using this kind of building block. And we call this our DCM, that's a DC converter module. Now we take a couple of those DCMs and we put them in parallel, or we take 4 of them and put them in parallel, and you can see from our technology demonstrator here, we can have a very, very small and light converter. So this is a 1.8 kilowatt high voltage automotive voltage, and it's say nominal 330 volts, but it could be 160 up to 420 volts on the input, down to a 12 volt standard car battery. Very high efficiency, we're doing 93.5% peak, and you'll notice from the simple drawing on the right hand side, due to the modular nature, we can invoke what we call the eco array mode. If you're running at 10% power, you don't need all of the power modules to be switched on. So why not just use one of them and enjoy the benefits of a single device's efficiency curve? As you crank up the power, more and more of those modules kick in until you get all 4 running at full power. So this is, again, another way of flexibly using these power components to create different systems. So that's a very high-level look at some of the auxiliary power modules enabled using these modular approaches. Now, on the penultimate slide, just as a thought-provoking question, is why stop at a hybrid? Why not go to full electric power? So obviously, a lot of these elements are market-driven. Some of them are environmentally driven. Some of them are the elements of the market being consumer selection, the pricing, and availability of different technologies. But something to give you some bedtime reading is a report. It's a little old now. It's a 2010 report from the Oak Ridge National Lab and the Department of Energy, looking at why a full electric would be a good idea. And so they've done some results, and I think it all comes down to the W2W, which may be a new acronym for you. That's well to wheel. So in other words, from the moment you're pulling crude oil out of the ground to the moment you turn a wheel going down the street, what is the energy efficiency of an internal combustion engine versus an electric engine? Obviously, internal combustion, you need to pull it out of the ground, transport it, refine it, transport it, load it into your car, burn it, and then the car moves. In an electric car, you have to burn that in a power station, which might be more efficient. You still have to transmit that power and then charge your vehicle and then turn the wheels down the road. So an interesting parallel. And so I would recommend this for background reading, this report from the Oak Ridge National Lab. And that rounds out our presentation today. So far in the series, this is number 7. We started off with some background information and then went into some specialized presentations with some guest speakers. And very pleased that we'll be able to round out the series next week with the U.S. Army RDECOM, there's a slight typo there, for the next-gen combat vehicle. So very excited for next week's presentations. Now, so far, seminars 1 to 6 are already recorded and online on vicorepower.com. I'd like to thank you for attending.